Friday night engagement with my daughter. I have to take her to Kung Fu in the night. So unless a world war comes, we don't miss the Kung Fu lesson. So I have to accommodate my daughter in that regard. Okay. Great. Students are trickling in. So Jntuk, we go ahead and put a nice quote somewhere in the chat. Okay, I think people are down there at Pragati. While you are trying to put a nice quote there, where we left off was we said you are working on this traveling salesperson problem, and we went through that, how to use the techniques of solving TSP using branch and bound. And then I went through each and every step in doing a similar problem. Then I asked you to work on that, right? So there are two things that we do today. At least I hope to do two things. If we do one or one and a half bit, that's okay. We can continue in the next class. We are not in a rush there. Okay? We'll go. Growth is the only evidence of life. John Henry Newman. Very nice. I never heard of that quote. I should look it up. Who is John Henry Newman? I'm just googling him. John Henry Newman. Very nice. That's a great quote. Thank you. Okay, so going back to Christian doctrine, okay, Catholic scholar, okay, that is true. Okay, so that kind of made me awake. We are all growing here, by learning all the new stuff. There is an interesting corollary to that, right? If you stop learning, check out, maybe you may be dead, Danny. It's like go to there. Okay. If you learn, you grow. Okay. So we'll revisit our problem. We'll see how we can action bound there. And James Bond, you only live twice, Antarwood. You only live once, but if you do it right, once is enough. I don't know if I have a great lunch with Aishwarya Rai or somebody like that. Maybe I want a second time around too with them. So it all depends. Of course, I wouldn't say that in front of my wife. Okay, branch and bound. Let's jump into it. But before I jump into it, do students have any questions? Are you hanging in there? Anything that I can answer? Nice quote, absolutely. Nice quote. He always gives fantastic quotes. I should stop giving quotes. All I can tell him is, okay, you give quotes every class, right? Okay. So knapsack problem, we have considered. If you notice something, all these algorithms are the same old problem spaces that each of these algorithms considers, right? That just shows like how we can apply algorithms to those problems to keep improving, right? So we know what the problem is. You have input of capacity K, you have n items with some certain weights and values, and you want to fill the knapsack, right? Where you have two conditions. One, you cannot exceed the weight of the knapsack. Number two, the sum of values of items is maximized. That is the broad concept. Getting some static, please mute yourself. Go to REC Jntuk mute. SVCW, I'm muting you. Okay, great. So we know that knapsack problem. Okay, and we have seen this too, right? We have seen this movie before, as they say in this country, right? Greedy doesn't quite work. And then we have considered those coins problems and all of those things to show that we don't get an optimal solution. Okay, so we'll figure out what are the ways in which to solve this, right? Okay, and then you also have the question, oh, today is Happy Women's Day, huh? Oh my God, we should have celebrated. I'm so sorry that we did not. Oh, it's tomorrow for us, that's right. So Happy Women's Day to all the fantastic girls in this class. It reminds me when I was doing my engineering, there were 50 boys and 2 girls in the entire. Actually, 2 girls in the entire all 4 branches combined. Actually, or maybe not. 2 girls in electronic. You can imagine the tough competition, right? In high school, women are beating boys like crazy all over the world right now. I don't know if the boys agree with me or not, but that is a fact. Okay. Continuing, when we talked about knapsack problem, right, most of it we said 0, 1, we can't do fractions and things like that, okay? But what if we cannot describe our problem with integers? Here is an example, right? You have weight of A, element A, weight of E, which is pi is 3.14 anukunta kada. Weight of C 1.98, some fraction of C. So how, and then there are certain values here. So how do you solve this problem? Okay. Now students, if you notice in the process of doing these problems, you are kind of relearning what you have learned too, because it's this problem domain but different ways of looking at it, right? So it's actually good for you. So look what this guy does here with this problem space of knapsack. A, B, C, D, E are given, and those are the elements with certain values. Somewhere I think the weight of the knapsack cannot exceed 5 pounds. I forgot to write it somewhere here. I think it is 5 pounds. Okay. Now, how do we do it with brute force? Brute force, by now you know we can generate all the possible solutions, right? So if there are n items, there are 2 raised to n solutions. Okay, and then we can check which of those solutions satisfies the constraint, right? And take the maximum solution that satisfies that constraint. And we already said that we can represent this using a tree, right? Our favorite guy, tree, right? Tree works quite elegantly for these types of problems. Okay. So here is one way of branching. Okay. What did he do? He started at A. Okay. So that means A is in the knapsack. How do I read this? I did not really pay too much attention to some of these slides. I hope I am saying it right. If I make a mistake, faculty members, please correct me. Okay. I'm losing my voice too. Okay. So if the A is in, then after A, then B is in. Okay. Then you have 2 branches, right? Actually, at every node, let me backtrack. At every node, from if you start from the root, it's either in or it's out. Correct? How do you read it? A is in, the A is out, 2 branches. Then after A is in, then you say B is in or B is out. Then you come to C. C is in or C is out. Then you come to D. D is in or D is out. Okay. Then you can come to E. Okay. So when you go through each of these branches, 2 raised to 5 together, 5 elements A, B, C, D, E. 2 raised to 5 is 32. Are the leaves 32 there? 1, 2, 3, 4, 1, 2, 3, 4. Yeah. So leaves, if you see the things here, leaves are 32. Okay. That is your brute force branching space. So each of the branches you add the weights along the path, right? And then you see the value. Got it? So depending on which path you take this big branch 2 raised to 5. The problem, what is the problem that you see here? Because remember, the brute force means you build the entire tree, right? Now by the time you build the entire tree, what is happening here? The weight is exceeding, right? By the time I see here, like here I see the weight is 15.12. So it's a waste of time and space, right? Computing time and space. When you know you cannot exceed more than 5 pounds, what is the use of building the entire brute force branch? Doesn't make sense. Okay? That is where we said in the brute force backtracking would be good. Remember we talked about backtracking, right? Like same thing. Go back to your n queens problem. N queens problem, what did we do in backtracking? We did a depth first search. The moment the constraint is violated, we backtrack, right? So we talked about the concept of promising nodes and not so promising nodes. So the essence of the backtracking is that, right? So when the solution is no longer feasible, no need to continue exploring. Unlike in brute force, right? So you backtrack to the node where the last successful node, then you take the other branch. Okay? No. So ikkada one second, I want to check something. So here is the same similar tree. As you are doing it, when you see the value exceeding, you come off. You don't build a full tree. You can see here some of the branches, they are not fulfilled. Just an illustration. Right? So since you are backtracking, you are no longer traversing the subtree related to the node where the rule got violated. Okay? So when do you backtrack? You're backtracking because your current best solution, whatever it is, right? Okay. So if the solution that you come up with is worse than the current best solution, you backtrack. So he gave certain ordering there. If you notice here, the way the best practice is, he gave certain ordering here. He goes in a certain order, he builds the tree, and then you apply the backtracking techniques. Okay. He gives an example. Based on the ordering that you have, he comes up with a value. Remember, you can each path of the tree gives you a certain value, right? So he follows that. So saving is better than brute force. Okay. Now what happens here is, as soon as you choose D in the first branch, we are already overweight. Which is D here? D is this one. D is 5. So it has to be, the knapsack has to be less than 5. In a slide, I think in the beginning I mentioned it has to be less than 5. The advantage, at least here, is that depending on what you select, you know when to stop and prune the tree. You don't have to follow the rest of the path here. Okay? Because we don't need to take that path because it's not going to do an optimal solution. Now, how do we do better? Let's look at it. Right? That's where we get into this drag and bound that we talked about right last classes.
I don't know how we are going to resolve
The trick, of course, is that remember in the very first class I mentioned, how do we get an initial bound? I mean, there are no...
Yes.
If we already know, if it is science and we know what is the best way, then there would not be any research. Right? The very fact that there's a lot of research still going on should tell you this is more like a heuristic, right? It's like an educated guess. So in the case of NAP,
but if it doesn't happen, I will
how
show
do
you
we
what
generate a good initial bound? That is the question. Because if I know the good initial bound, then I can build a tree accordingly, keeping the initial bound into consideration. And then hopefully I can arrive at a solution sooner rather than later. That is the idea here. So, if you look at our state space, okay, knapsack, there is no ordering of the items. You know that, right? We can put any item that we want. Sorry, I'm losing my seer. Let me have some tea. What are the options that we have? In the beginning classes, we learned about highest weight first, right? Remember? We take the highest weight first. Okay. Advantage by doing it that way, you can cut off the subtrees faster. Right? The moment you exceed the weight, you can cut off all the branches underneath that. Okay. Good. One weight is good. But one weight back, right? If the highest weight has the lowest value, what good does it serve? So there is a thing called highest density first. Density is more like a biggest bang for your buck. That's what we say in English terminology, right? What gives you the big bang? Big bang obviously in our case would be to say that you want the lowest or highest value. Okay, it's like that ratio is good for that. Okay, so he is considering. So remember, this is your data set, right? Okay, keep that in mind when you get the data set. Okay, so here is an example of highest weight on top. Okay. So when you do the highest weight on top, if D is out, you can see what is the value of the remaining items here. Let's say D is out in that branch. If these things go there, the maximum remaining is the value is, if you add up these things, it is 100, 140, 170, 220. That's how this 220 came about. Okay. If D is in, then you have B, E, A. You can count all of these things. Some are in and some are out. Okay? And you can see how the tree is constructed. I'm not going into each and step here because by now you know how to draw a tree, right? We have drawn enough trees. Okay? And then at the leaf node, you can consider the weight and then the values. Okay? That's the heaviest on top approach. Now let's see what is the best density on top. So how is he defining density? I mentioned here, right? Biggest bang for the buck. If you take the value C here, okay, 1.98 and the value is 100. If you take the ratio, that is 50, right? If you take the ratios of value to the weight, if you compare all of these things, C gives you the best value, right? The second one gives you 20, third one gives you 15. Fourth one gives you what, about 14 point something. Yeah. And this gives you 30 or 310. Now by doing this, if you notice, right, what is it that these two slides are showing? They are basically showing you your state space tree. which one is looking more dense? This has more things done, right? So you are going to traverse the route deeper, and then it requires more storage, whereas this one is a little bit more sparse compared to the previous one, right? That's another approach to the knapsack. Okay? So you're applying some get out of that. Okay. Now there are other ways to that. Okay. There are situations where you can combine both the greedy and brute force. Where does this come up? Let's say half the inputs to a knapsack problem have all the same weight. Meaning, I mean, very rare, right? Why? Think of a situation where that can happen. I'm sure there are situations in let's say in a like operating system when I'm scheduling tasks that this could become relevant. Okay. So if you have a case where if half of the inputs are the same weight, but since other half do not have the same weight, right? So on half of the situation you can apply a greedy solution. And on another half of the situation you can perhaps build a brute force approach. Okay? So what it tells you basically is to solve a problem. This is what I call it, like my professor used to tell me. It is not the case that you only apply one technique to solve a problem. We call it what is known as a multi-paradigm approach. See, there is a saying in English, you know, if you hold a hammer in your hand, everything looks like a nail to you. It means the guy only knows one thing. But here what we are saying is, yes, these are all different techniques. Depending on your data set, right, you can determine whether one approach would work or a multi-paradigm approach, multiple algorithmic approach. Little bit theory there. If you don't understand, I'm not too worried about it. I don't think in your exam they would ask you, show me an example of combining greedy and brute force. To my knowledge, they don't do that. When you are doing that technique, one half you are applying greedy, the other half you are applying brute force. Different ways, right?
Final version of
For graduate class, it's a legitimate question to demonstrate this, by the way. So by doing those things, why do people come up with these kinds of techniques? You can see the idea is to reduce the ego, right? So by doing just the brute force, you have to build a tree which is going to be a factorial 2 raised to n. We already talked about, right? So by combining the techniques of both brute force as well as greedy, you can see you basically reduce 2 raised to over 2. Big, significant difference, right? Of course, n times that one. And n is greater than 2 or something like that. The value you will see how much better that would be, right? Here is a good example of that. If n is 50, and we are assuming we can solve 1 million solutions per second, okay? 2 raised to 50 is 35 years, guys. Half of your life is gone, you know? Okay? Whereas by combining 2 raised to 25 can be generated in half an hour. Okay. Actually, I was taken aback when I looked at it. Is 2 raised to 50 really 35 years? Somebody needs to verify that. And then by reducing it to half, it only comes to 30 minutes. See the power of algorithms there, how to optimize that? Extremely efficient, right? Where is half an hour and where is 35 years? That's the reason why people who are good in data structures and algorithms, they can command a lot of money. Okay. The other combinations and permutations and combinations, right? Some have integral values, some have real values. Again, I always say that you have to be creative, right? You just have to figure out what is the right approach to take here, right? That's why, I mean, all of these things I can actually call them as dynamic programming, you know, because the essence of dynamic programming is creatively solving the problems, right? Okay. Same thing, we talked about the n queens problem. Remember, I made you do the 4x4, right? We know how to approach the n queens problem. Another classic case here, when you do it with respect to n equal to 4, you can see you're placing the 16 square board, right? 4x4. So you can see there are solutions which can be like, to place the first queen, you can place it in any of the 16 squares, right? Second queen, one less, right? Third, one less, because the square is occupied by queen. Fourth is 13. So you have 43,680 possible solutions. Possible, they are not right. They are only possible. Okay? Now, once you start putting, you already know the constraints, right? When you know the constraint, by taking advantage of constraints, if you do brute force, right? This many solutions. Okay? If you give it a smart guy, says, I can only place one queen per row. So all of a sudden your solution space is only 256 possible solutions. Okay? Now this can be reduced further by applying backtracking techniques, because once they attack, you backtrack. Remember, we did that problem. I made you do the pictures of that. So that is the advantage. Some of these advanced techniques. Some additional data for you. If it is an 8 queens problem, what is the solution space? It's basically humongous. Okay? So you have to be smart in terms of applying the right algorithm. You cannot simply write for loops for each and every row and every column. If you do that, then you will end up doing all the 16,777,216, whatever that big number is. Okay, so enough of that. Okay. Questions, comments, because we are going to do a group exercise now. I don't know if I said group exercise, we do it like, did I give any time? Like, I think we'll kind of do it as a group together. We'll do another exercise after I complete rest of the material here. Okay. Let's look at a group exercise problem here. For those of you who fell asleep listening to their only slides there, this will wake you up. So in the US, because this is a classic knapsack problem. See, ultimately you would apply. Actually, I'll make you apply this. I'll make you do it first, okay? Then we'll discuss it as a group too. Okay? Turn on your videos. Gather yourselves in groups of 3. Okay? Get out your paper and pencil. Solve this problem using some of the knapsack techniques that we talked about. Okay? What is the problem? Let's understand the problem first. So US has a big navy. India has a navy, right? And in US you have these SEALs are like SEAL is an acronym actually, I forget what it stands for. But they are the top-notch guys in the military. Military includes, Navy, Marines and all that, right? They are the guys who went and... Okay. Now, so we are putting together, they all have skills, right? And then they can do different types of missions, okay? So what we have here is a classic case of K different skills needed for a mission. I'm starting a mission as a commander. Okay? And then you can assign N SEAL members that can be assigned to the team. So what is the smallest team that will cover all of the required skills? Okay? Sounds it's easy to understand, right? All we are saying is we have people, and then each of them has certain skills. And then I want to put together a team. Okay? And obviously, what is my objective function here? I always want to save cost, right? More resources mean more money, right? I have to pay more money. In a, simply speaking, okay? Before anyone contradicts me on that. Because I can also say I have to pay more for a guy who has more skills too. Okay? But let's assume they all have, like in India government, all professors get the same amount of money, with a certain experience. There's a formula there. Okay? The problem is we are putting together a mission. We have different people with different skills. What is the smallest team that will cover all of the requirements? That is what we want to do. Okay, so these are the 1, 2, 3, 4, 5. Take down on a piece of paper, write these things down. Okay, I'll bring back the slide here. Okay. But what I want you to do is, what is the obvious greedy algorithm for this problem? I want you to answer that. Okay, and then I want you to also answer, find a counter example of the optimality of greedy for this problem. We did something similar earlier in the case of coins, if you remember. Because then we are going to apply, I'll put this here. Oh, I don't have room there. Now, exercise 2, it's kind of like a big exercise. I don't expect you to do it all in the class. But what I want you to do is, right, just to get practice. Okay? You don't have to solve the full problem here, right? Just to get practice for that. Applying the brute force approach, draw the tree. Okay? So how do you draw the tree? I showed you how to draw a tree, right? If you go back here, let me show you the tree here. Draw a tree and all. In and out. So this in and out, I don't know whether it's a person or it is a skill. You figure that out. Okay. Draw some. You don't have to fill out the full tree. I do not know how much time it takes to do the full tree. I did not do it myself, so I would not know. Okay. Is the scope of the problem and the exercise clear for the next 15 to 20 minutes? Okay, is there any student who does not understand what is required to be done? Is it clear to the faculty members who facilitate this then, who have to facilitate this? You have skills, you have people, find the team, smallest possible team that will cover all the required skills. Okay? Now, in the process of trying to do that, apply your greedy algorithm. What is the greedy algorithm that we can apply there? Remember, we are improving our greedy to brute force, to backtracking, to branch and bound. I think I said it right. Greedy to brute force, to backtracking, to branch and bound. That's the eventual thing, right? But to get your feet wet, what kind of greedy algorithm you would use? List it down. Okay. Later on I'll ask you why you chose that one. You should be able to explain. If you can find to the greed, remember greedy doesn't work, right? We already established that. If you can find a counter example, that would be great. If you don't waste time on that. Okay? Do this one for sure, and then go to brute force approach. Build a brute force approach tree. Again, you don't have to build a full tree, just go 2 or 3 level deep. Okay? Now, once you do that, then we will reconvene, look at what you have. Okay? Then we'll see if we can collectively I don't have any ready-made answers, by the way, guys. I'll be doing it along with you. Okay? We'll take your faculty members' help there. We'll together solve the question for the 4 bullets. The legitimate final exam question, by the way, at least here in this country. Okay? There's nothing to memorize there, right? It's all about thinking. Okay, faculty members, if you have any questions, comments. Okay, ready, set, go. I think it's fair to give about faculty members, please facilitate, write this down on a piece of paper, so that way I can put the question there. Okay. I can even remove this for now. Okay, let me see. And then I'll say, I'll take this question there. I will put it here. ఓకే నోట్స్ పేజ్ వ్యూలో పెడితే ఈజీ అవుతుంది అది. లెట్ మీ సీ ఇఫ్ ఐ సే వ్యూ 2 slides at a time. Not notes page, what is that? Handout master kada? Yeah, if I do handout master, sorry, I tried. No, I can do two slides per page. I forgot how to do it. Okay, back to normal viewing. Oh, turn on the video so that I can enjoy watching students doing the exercise for the next 15-20 minutes. And if you have questions there, put them in chat. Actually, I can put the questions in the chat. These are the 3 questions. Yeah, I can put them in the chat. Those are the 3 questions that you need to answer for this exercise. Okay, why is everyone so quiet? You can turn on your videos so that I can see all the students working on it. Perfect. Do you understand the questions, students? Do you have any questions? Ask your faculty members to put it in the chat and I'll answer them. You should be in a position to explain to me the greedy algorithm there and as well as the brute force approach. How you would take a brute force approach to build the tree. Time now is approximately 11:33. 15 minutes puts you at 15 to 20 minutes. I'll be fair to you, okay? I'll put you at 11. It's not 11:33 for you, right? So about 11:48 to 11:50 your time really. And look at some solutions. So if you are into movies, guys, I saw this movie, Telugu movie that came, Kalyana Vibe Okame. Nice movie. I'm sure young students would enjoy that. I can see Chaitanya, I can see ASET. ASET, you missed a couple of classes. Chaitanya, you missed a couple of classes. Whatever happened to Sintans Chirala? They miss a lot of classes. Pragati is quite active. Okay, I can see your video. The number of students in Jntuk Kakinada, are they sitting on the other side too, or because the camera is focused only on one side, I only see like half the students, I guess. Okay, faculty members, give me some feedback in the chat. How are the students doing? Faculty from chat lo pettandi, your audio is not so clear. మీ ఆడియో క్లియర్ గా లేదు. కెన్ యూ పుట్ ఇట్ ఇన్ చాట్? Somebody asked me, can I put the PowerPoint in the share mode? I will. After the class, I will do that.
నేను ఫస్ట్ ఈ ఐడియా హెడ్ క్వార్టర్స్ రాస్తాను. క్యాన్సర్ చేయమన్నారు 15 టెక్నాలజీ నాకు తెలియదు. నాది క్యాన్సిల్ చేశామంటే మాత్రం ఎందుకు చేశాక నా లైఫ్ లాంగ్ బాధపడేలా చేస్తాను. ఐడియా నంబరు మామూలు ఇది సబ్మిట్ చేయమన్నాడండి. ప్రూఫ్ ఫోటో అది ఇచ్చాను. కంపేరింగ్ కూడా పడేసాడు.
How are we doing? In a few more minutes. So please share the question. Okay. Yeah, the first question was, actually I put the questions in the chat. Did you see that? Chat window. I put the 3 questions there. Just go up, scroll up. These are the questions. What is the obvious greedy algorithm for this problem? These are the 3 questions which I'll put here again. So what is the obvious greedy algorithm for this problem? What is the brute force approach? How do you suggest a brute force approach, right? I just wanted them to think and draw a brute force tree as an illustration, similar to how we have drawn the brute force tree. I will show the brute force tree that we have drawn, so that way you can draw it similar to that. So ఇక్కడ ABCD were the items, remember? certain weights, right? What is the first one in the bag? That is the A. First one in the knapsack. So to give you a hint, here you can say first one in the team, right? Or knapsack is the team here, right? Knapsack doesn't have to be bag literally, okay? It's a concept, right? So first one into the team, that could be one of those guys, A, B, C, D, whatever I gave the names there, right? Like that you are building the tree. Pretty straightforward, right? Okay. The reason I make you do this, students, in case you're wondering, right? Staring at your, if 80% of you must be staring at a blank sheet of paper, not knowing what to do to begin with. I would much rather you feel lost in the class, not in the final exam. That is why I make you practice these things. So that way you get a working knowledge as to how to get going. Given a problem, how to start solving it. So all this practice would help you for not only exam but real life scenarios. Okay. As I said, I don't have any, I didn't solve it. But I mean, I had a class of problems, this one. So, if anyone has answered to the first question, what is the obvious greedy algorithm for this problem? By all means, you can either talk if your audio is working, or you can put it in the chat. If you want to talk, you can unmute yourself and present it, okay? You can take the board away from me and you can present it. Or if you put it in the chat, I'll share it with everyone. Either one would work for me. Faculty members are welcome to take a stab at the solution. Faculty and students. Let me simplify the question, if that would help. What are the criteria that we could potentially apply? Greedy means who is that first guy, first thing that we are going to pick. So do we pick Anderson? Do we pick Butler? Do we pick Cunningham? Do we pick Douglas? Do we pick Eckers? Maybe వాళ్ళని మన తెలుగు పేర్లు పెట్టాల్సిందేమో నేను. I should have So I'm looking at this wonderful set of girls at SVCW, first row. 4 girls I'm seeing. Let one of them come to the front. Somebody already answered. Okay. Now, Jntuk Kakinada, hold on. You answered that one. I wanted to focus on girls here. Women's Day, right? Let's have some fun on Women's Day here, okay? And give them an opportunity. Jntuk Kakinada said they want to pick Anderson first. One of the girls that I'm staying. Why do you pick Anderson first? Did you pick Anderson? You worked on the solution, right? Who did you pick first in your solution? You have a piece of paper that you have written these things on, right? Madam unda mi madam akkada lekapothe inko student ichi meeku anistonna tana sheet. Okay, go ahead, speak. Don't be shy. Tell your name first.
He has to authorize whatever lesson. We can't write something like this. Money had no problem. That's supposed to be. And
Excellent. That's leadership. Go ahead.
Good morning, sir. My name is Ii
Excellent. Go ahead. What did you have as an answer? Who would you pick? You will pick Anderson in the greedy approach first. Is that what you said? You pick Anderson. That is the question. No, Anderson King, see, Anderson only has 3 skills, right? Whereas Douglas has 4 skills. So why would I pick Anderson over Douglas? Jntuk Moocs, you also said Anderson, but why would I pick Anderson first? I would pick Douglas, right? It's a no-brainer. Am I saying something wrong there? So once you pick Douglas, then you can see who else can provide the rest of the skills, right? He has more skills. According to greedy approach, we choose the present best optimal one. So we have not chosen anyone yet, right? Yet. I just gave you that. So I didn't say choose some candidate, right? I just said how would you apply the greedy. So I still do not see the reasoning that you are giving to pick. If you think Anderson is the first choice, I see Jntuk Moocs defending that. But the present best is optimal one. Present best is, I don't know what is the present best, right? Unless I'm missing something. That's a good point. The reason I'm discussing these things is I want students to develop that critical thinking. Okay? And solve. Now, between Anderson and Douglas, you cover all the skills?
Yes.
Oh, no, okay. Because now, how did you determine that? Did you draw a small, like a chinna table laga? You probably would have drawn a small table of skills, right?
I'm using paper and maybe
Got it. Okay, excellent. Fantastic. I'm glad you are taking comments. That's how everyone. Good job. That was good. Okay. Now, let's take a couple of more questions there, right? What is the question I wanted to ask you there? If I change the problem slightly, if I say Anderson costs 200K, Butler costs something, would that selection of the greedy thing change in any way? Based on what you learned in the class today. Remember, you always say big bang for the buck, right? So if I say, let me put it this way. If Anderson costs $150,000 or about 2 lakh rupees, okay? Anderson costs 2 lakh rupees. 1 lakh rupees per month, okay? And I'm getting one extra skill. Then I would choose Douglas over Anderson, right? If all things are equal. Isn't that what is happening in offshoring all the jobs from Silicon Valley to India? Right? I can write a Java program here, but I'm also paid 100K, let's assume that. I can get the same Java expertise in Infosys or Wipro or the now defunct Satyam. If you know who Satyam Computers or was, is. It's much cheaper, right? See how the small adding one extra variable changes your knapsack. I mean, all those things are knapsack problems, right? Why am I giving this example? To tell you, knapsack doesn't in marbles and sweets and things like that, or a thief. You apply knapsack in every aspect of your life. It's all about optimizing the value, right? Biggest bang for the buck. Okay? Kind of like in the olden days, the marriages between kings and prince and princesses used to be based on knapsack only. Who has the clout, who has the money, right? You want to marry the princess who has. Let's go to the second one here. Yeah, Jntuk Moocs, you got it. We can apply knapsack with the highest weight on top, then we pick that less. Perfect. Highest weight is nothing but the maximum number of skills. You got it. Okay. Good. The idea is, see, Jntuk Moocs, what they have done, even though they have chosen the other one, right? They are actually thinking, right? I'm just illustrating, not that others are not thinking, but they're justifying how they have gone about, right? So that is the discussion that I want in this class, right? There is no right or wrong answer. You should just be able to defend yourself, that's all. Okay? Okay. So when you do a brute force approach, right? So what is a brute force approach to this one here? You're going to draw a tree basically, right? Brute force and you have to look at all the permutations and combinations. That's what it is, right? Remember, the brute force for a 4 queens problem is what? You had 16 times, 15 times, 14 times, 13 times, right? That's all possible solutions. Because initially when you have 16 pairs, it's 15. So you can place the. So if you take. Anyone knows what total. I did not figure it out, but if anyone has some answer, you can put it there. I'm just thinking like that. How many skills are there? The brute force would be 1, 2. Is it really is the brute force based on the number of people, or is the brute force based on skills, or is it a combination? I don't know that. Honestly, I don't know. I don't know what would be the total number of solutions in brute force. If somebody can figure out what the total number of solutions are for the brute force, either put it in the chat here or put it in the community. Okay? Then we'll all. Let's give an opportunity to some other college now. Pragati, you want to show us a tree? If you have a tree that you have drawn, you can just put it for the camera and we can all see that how the tree looks like. Pragati, or where is I'm looking at the colleges here, see who has more girls there, and I'm picking on them. Yeah, we'll go to permutations of size 1 to n. To show us, to draw a brute force tree there. This is exciting stuff, guys. I'm so excited now. I lost all my. I don't feel sleepy at all now. Tree, okay. Now I'll open it. I'll open the floor to all the colleges, has anyone drawn an illustration of a tree? Remember I told you not to draw a full, show me how a tree looks like. I wanted to see that starting point and remember like 2 level or 3 level deep. Or you did not have enough time to do it now. Okay. Okay. Jntuk Moocs, I thought somebody would come forward. They didn't. Okay. Is there anyone who has drawn a tree? If not, that's okay. I'm not too worried. But what I want you to do is, right, go and start drawing a tree for that. Because believe me, this is a legitimate question in final exam. If you don't know how to draw a tree illustration, then you will be in big trouble in final exam. Okay? Take this as an exercise for home. Okay, let's move forward. I'm glad you did. Right? I want you to answer the rest of the questions there. That will prepare you well for greedy, brute force, backtracking, and branch and bound. Everything in one problem. Okay? Okay. Now, if you look at the syllabus, another aspect of branch and bound is typically whenever we want to identify solutions, right, we always have some objective solutions. From a business speak, what it means is you want to reduce costs and increase cost solution. Even if you look at the traveling salesman problem that we did, right? What did we say? We have to go from city A to B, C, D, E, F, G, H, and come back to the source. It's either in the least amount of time or with the least expensive amount, right? Either a low cost or low could be cost, low could be time, any of those things. So how do we do that? What is the branch and bound algorithm where we are determining the least cost solution? Because our bound, basically this is our bound. The bound is you're choosing a path which gives you to the question here. SVCW said that. I'll put that here. SVCW, with your permission, I'm putting it here. Remember I told you, that's why I said I would much rather you face difficulty in the classroom here doing these exercises rather than trying to figure it out in an exam, right? Okay, that is SVCW statement. Think, I'll make you think a little bit. You'll be able to come up with some tree. There are not too many options. You there. It should be, there are so many different ways of drawing trees, right? Think about it and you can in the community, okay? That's a food for thought for you after the class. Okay. I'm sure each one of you have solved this growing up as kids, right? Remember that puzzles that we have where there's always one number that is out of sync and you have to arrange them? I remember doing it in like my second grade or something like that. And then let's say the one that we go to exhibition grounds and buy like in a fair. Exhibition grounds is like the fair, right? And, we are always fascinated. One number is out and we always want to solve it quickly. Okay? I'm assuming you are able to see that. Let me put it in that mode there, okay? This is what we are doing through this example is we are trying to do the least cost approach to solving a problem. Okay? In the context of branch and bound, obviously, right? The bound is that cost. So if you notice, my initial state it is this one. My final state is not the completely solved puzzle. I did not say solve the full puzzle, okay? By the way, if you're taking down notes on this, don't worry, I'll post it in the community, okay? Sit back and relax and listen and enjoy, okay? Don't need to take notes unless you need some things. Final state. All I did here was 1, 2, 3, 1, 2, 3, same, 5, 6. So I want to get 8 here, and then I want to move 6 here, and then I want to move 7 here. Okay? Don't ask me why I want to do it like that, because it's some intermediate state, okay? Now how do we get to that? That is the main thing, right? How do we get to that is the main question, okay? Now how do we formulate our cost function to do that problem? Remember, cost could be taking the least amount of steps too, right? But every step has a cost associated with it. That's why we call it least. So we call it least cost. Directly, when I did the tree problem last week, I actually applied the lowest cost problem in solving. If you go back to the slide that I posted last week in TSP, you would see that. Okay? Now, the way cost function is defined is Gx is, remember what was the cost function there? Gx plus Hx, right? So Hx is nothing but the number of misplaced tiles, and the Gx is the number of moves so far. Okay? Okay. And then we are also making an assumption that moving one tile in any direction costs 1 unit. Okay? To keep it simple. Okay? This is the problem domain. Did I miss anything there? Let me check. Okay, I'm so far so good. Okay. Now again, you will understand the cost function slide, I think. So what are we doing with for 3 things here, okay? Can someone tell me in the chat why I put these 3 things here? How did I arrive at these 3 branches here? The first function is the cost of moving. Okay, go back here. The Gx is the cost of moving. Misplaced tiles up there. Okay, note these 2 things carefully. Cost of moving, and then how many misplaced tiles are there. So he is assigning meaning to Gx and Hx. So in the case of tiles, solving this problem, it is misplaced tiles. If it is some other problem that you are trying to solve, that misplaced tile has to be related to your problem. Okay. So you have to formulate that function like that. So let's go here. This is super exciting stuff. Huh? See, because it's online, I usually have to terminate the class on time. If I'm doing what am I doing here in this one, let me blow it up. So what are the possibilities of moving here? I can move 4 up, correct? So move 4 up is this one here. See this one on the leftmost subtree? 4 moved up. Okay. How did I calculate the cost here? I moved 4, right? That is cost of moving, that is 1. How many misplaced tiles I have at that point of time? Say misplaced means they are not in the right position, right? So 1, 2, 3 are in the right position already. 4, 5, 6, 5, 6, 4 are and then of course the last one, empty one. That's 4. You get 5 there. Okay. When you put the 4 to that second row, third column. Now, what is the second branch here? Why did we get cost equal to 1 plus 2 equal to 3? You moved 6. Okay? So when you move 6, that is cost 1. And what are the two misplaced tiles there at that point of time once you move 6? Quick, 10-second answer. The two misplaced tiles are 4 and 5, aren't they? Right? 4 is supposed to be here, but it's here. 5 is supposed to be here. So Jntuk Kakinada, I think it's 1 plus 4 కాదు 1 plus 3 అంటున్నారు కదా మీరు, అది లెఫ్ట్ సైడ్ మిస్టేక్ టైప్ ఉందేమో అక్కడ. థ్యాంక్ యూ. దట్ షుడ్ బి 1 plus 3 equal to 4. Got it. Got it. Okay. Now instead of 6, what did we do here? We moved 3, right? These are the 3 options, right? You can either move 3 to this one, or 4 here, or 6 there. That's why you got these 3 branches. Okay. So when you move 3 there, 1 is constant because it's 1 move into 1 square, immediate square, adjacent square. Now once you move 3 there, how many tiles are out of place? You have 3 out of place, you have 4 out of place, you have 5 out of place, and you have 6 out of place. Okay? So you have 4 tiles which are out of place. Got it? Okay. Now you tell me, what do we do next? Guess. I want you to guess what. Remember, we are discussing this one, branch and bound, with the least cost philosophy, right? So, from a least cost philosophy, what is the next step that we take here? Because we are building that full tree, right? So, which branch follow here? That is essentially the question, right? Cost approach, we follow the least branch, least cost. Least cost, because I put a cost factor to it. Earlier I did not write brute force, I have not put a cost factor. Whereas in branch and bound, I start putting a bound, and my bound here is the cost. So, I would take the middle branch here, right? Because the cost is 3. Left side branch is 4, right side branch is 5, middle one is 3. So I put 5. Middle one is 3, so I am going to take 3. So how would 3 look like? See, if I have I redrew that branch here, because if you see this, if you go back here to see this one, this is a branch we're taking where you have 1, 2, 3, 5, 6 like this, 7, 8, 4. Okay. So you take that branch and then you again see the cost of moving. What are the options of moving? Here you can move 8 here, or 7 here, or 4 there. Okay? Then you can compute the cost. Because remember, cost is now you're moving tiles, you're keeping track of the cost as you keep moving. So you compute the cost again to those 2 branches. Okay? It looks like right sub branch is the one that is lower cost. So you come to this tile. Building it, you're moving these things, and then you're arriving at a solution, right? Is this the solution that we wanted? 1, 2, 3, 5, 8, 6, 7, 4? I don't know, let me check. Yeah, this is what we wanted at the final state, right? So we arrived at this final state by always taking branch with the least cost. Okay? Now the trick is to formulate this cost. That is the trick. Once you know how to formulate that cost function through different examples like this, right, then it becomes easy. Okay, questions, comments? Let me stop here for a second. Okay, now let me go here. this is the algorithm for that, guys. Those of you, remember I told you a lot of times I'm showing you algorithms in a class, right? We don't go through it, I explain it, but I want you to go convince yourself how the algorithm works, right? You can see here you keep track of the nodes that you're interested in, that is a live node. Live node is the that is the node that is going to be expanded. That is the live node. That's how we define, right? That's how we define the drop. I don't know whether you call it infinity or zero, whatever programming techniques you use. I wouldn't care. So you are choosing some branch, right? I mean, I'm not choosing some branch, right? I'm not going to go through each and every line of it. But convince yourself, basically there are two parameters. I'm not going to go each of the line. And then you check that one, and then the nodes, you always maintain them that you have one. Somebody asked a question here. After taking small further steps, make high cost, taking smallest steps, make high cost. After taking these small steps, make high cost. Point. That is the reason why you have now these algorithms. You can backtrack, right? The goal is to have the smallest cost, right? Remember, these are all NP complete or NP, almost NP. Remember, these are all hard problems. You have a problem. The idea is more information, like how did we do it in travel problem? I knew the problem is I maintained the distances from every node to every other. Right? So I was able to tell the problem optimally from a polynomial. Okay? Remember, I do not know the actual exact solution. It takes infinite time, right? It takes and somewhere in between node, we did that in TS. Could have a node which has excessive cost, then you are stuck to achieve. Good question though. If this is without having to do any backtracking, it's all in the same problem, and it's life would be easier. Okay. Okay. So you are seeing that somebody asked a question there. Typically, what is the basic essential difference between backtracking and branch and bound, right? So here is very nicely asked question. Just when I'm on that slide, that's great. So when you talk about backtracking versus branch and bound, right? What is the difference between the two? Number one, backtracking, you're doing a depth first. Okay. Here, in terms of search, you're doing a breadth first or the least cost. That's the reason I mentioned that last class when we did the breadth first search, we are typically doing the least cost approach there. Now, execution time, backtracking is certainly more time. And then breadth first, because you don't want to go deep and then figure out that doesn't work, right? By default, even intuitively, that takes more time. Okay? And then breadth first is supposed to take less time because you're trying to optimize it as you go along. Okay, now with respect to storage space, backtracking apparently takes length of the long of the tree, that is the order, Whereas in the case of branch and bound, I mean, we didn't talk about queues here, but it really depends on how big the solution space is, right? The reason why I use the notion of queues is ultimately, I mean, I'll introduce you a technique called FIFO technique, or the opposite of that, LIFO, where we use this concept of a queue, and it really depends on the size of the solution space. Okay? But in general, when you use the breadth first search approach, most of the time, I'm not saying these are all like universal truths, right? You examine fewer nodes, okay? Whenever you do the least cost branch and bound. Yeah. Now, other things here, backtracking may never find a solution if tree depth, in theory, right? Okay. And then we have this technique which you have not seen. I'll be covering that next class. FIFO. FIFO is first in, first out, right? Okay. Most of the time FIFO works because you find the solutions closest to the root. Remember a long time ago, several classes ago, we talked about these B trees, remember? When we said this, when they said to access disk, B trees access disk, the reason B trees are great is that L is very shallow. Because things, we typically, the depth of the tree tends to be shallower, and then we tend to arrive at the solution much faster and closest to the root. Okay? Because we are making an educated guess. If you see the third bullet point here, is we are making an educated guess. I say we are likely to have an answer. We need to have an answer. Okay, so you're even it's like doing your work in a. That is what this least cost. Prune off or eliminate the subtrees faster. That would be some pruning those trees. That's all we are doing here. Okay. Now, are you there? No. You know the maze, right? How you can enter and exit at a maze. I just kind of put another example there. How does the rat go from the starting point to the exit here? 0 stands for there's a road, meaning there's a path. 1 means there's an obstacle, right? How do you solve this problem? Okay, so the way you solve the problem is basically using breadth first search. That's what the least cost approach actually is. The least cost in this case is there's a road and there's an obstacle, right? There's an algorithm that I think I gave here. How you implement this algorithm? Convince yourself. Read through some of these steps here. Okay. First, I gave you the pseudocode there as to how to code for a rat in a maze. I don't know if they would ask in an exam. This picture here matches the algorithm that I gave you here. So if I were you, I would take a piece of paper and assign values. That's how we used to learn programming. We used to assign values, go through these steps, and build this picture here. Okay, correlate that algorithm to this picture here, and you can see here when you build it here, basically it took about 9 steps to go through that loop. Not much, right? Simple 3x3 space, and you will see that the branch that you take here is so. Before you come to the next class, I want you to actually understand this rat in a maze problem and what the author is doing there. Okay? Okay. Questions, comments? This will give you further insights as to how to build a tree. I wouldn't call this a tree, right? Is this a tree? Can you call it a tree? It's almost like a network, right? Tree has one root. Yeah, I think you can call it a tree, right? Yeah, because you are not going back. There is no loop there. Okay. Questions, comments. I'm here. I can spend some more time here today to answer anything else. Okay, let's go back and look at what they put here in the chat. Did I kind of answer your question here that somebody put here, Jntuk Kakinada? Okay, perfect. Okay. And if any other faculty member wants to add any additional insights on the differences, please share it with us.